Hello, I'm going to be working through a physics problem that I was having trouble with on the test. The first step in reading this and doing this physics problem is reading it all the way through. So we know that a golfer hits a ball so that its initial velocity is at an angle theta from the horizontal. The ball reaches the top of its trajectory at horizontal distance x top from its start. On the way down, the ball hits and injures the shoulder of another golfer located at distance d from the first player in the same flat terrain. As indicated in the schematic in the following problem, the effective air friction on the ball shall be neglected. Find the initial speed, vi, of the ball and the time it takes to change the top, for the ball to reach the top of its trajectory. Express your results in terms of appropriate combinations of known properties and physical constants, theta, x top, d, g. This g being the force of gravity, or the gravity constant. So, the first thing I'm going to do is I'm going to break up my speed, my velocity initial, into x and y components. And to do that, I'm going to be looking at this as my velocity. I'm going to draw a triangle, make sure it's a right triangle. And then we know that this is going to be in the x direction, this is going to be in the y direction. We want to find right now, we're going to look for our x direction. So we know this is the hypotenuse, which is equal to our velocity. This is going to be adjacent to theta. This is going to be opposite to theta. And so to find this, we're going to use our cosine. So our cosine is shown as cosine of theta is equal to adjacent over hypotenuse. Once we plug in hypotenuse as vi, then we can see that if we multiply vi by cosine, we can find what our adjacent is. We would do the same thing for sine to find the y component instead of the horizontal x component. So we know that our velocity initial of the x component is equal to the initial velocity times cosine of theta. And we know that the velocity initial in the y component is equal to the initial velocity times sine of theta. Now, the next step I'm going to do is I'm going to look at the horizontal distance. So, we know that the horizontal distance, and right now we're only going to really be looking at x top here. Excuse me while I erase this. So, x top is also going to be our velocity in the x direction times the distance it takes to get to the top. This is going to be given our, apologies, I'm not explaining this very well right now. What we're going to try and find is our x top. X top is given right here, and it's going to be equal to our position update function. So we're going to take our x initial, which in this case is going to be 0, and write that up top, and then we're going to add the velocity. Now, it's important to notice that we're doing this in the x direction, so instead of using our initial velocity, we're going to use our initial velocity in the x direction, vi x, times the change in time. Now we know that this is going to be our change in time to get to the top. We're going to use this variable, change in t, top. And we're going to plug in the relevant value for vix that we just found earlier, and for xi. So x top equals our initial velocity times cosine of theta times change in t top. Okay, now let's move on to looking at the y direction for a little bit. We're going to be looking for our velocity update function now. So velocity update, we're going to go with Vy final is equal to y initial, once again this is going to be 0, plus vy initial, in this case I'm using this to equal this as well, then we're going to do times change in t top, and then we also have acceleration for this one. The other one we didn't need to worry about it so much, so we're going to do plus 1/2 oh, never mind, I'm using the wrong equation for this, ignore me. I knew something felt wrong here. So, we're looking for our velocity in the y final. What we're going to do is we're going to use our velocity update function, not our position update function, to find velocity. So what that's going to be is going to be our velocity y initial plus our acceleration, in this case it's going to be negative g, times the change in time. Now if we plug in the values for this, our velocity at the top is 0, because if it was continuing to move, it would keep going straight up, and since we know that it stops here, this is the time where the velocity in the y direction is 0. So we have 0 equals what we found for our VIY, or VYI, minus g times change in t top. Okay, now we have some stuff to work with. We can find out our change in t top using this equation. We can move t top to this side, getting rid of that negative sign, and then divide by g. And so we can find that the change in t top is equal to velocity initial times sine of theta over g. Okay. Now, going back to our x side, we can use our x top equals velocity initial times cosine theta times velocity initial times sine theta over g. Zoom in here. We're doing this to find our x top as well, and then moving it to find our velocity. So, what we can do here is simplify this down into VI squared cosine theta sine theta over g equals x top, and then we can move everything over to this side, leaving v on its own, so we can move the g and then divide by cosine sine, and that'll give us vi equals the square root, since it was squared, of g times x top over sine times cosine of theta. And that's going to be our VI. Let me draw my arrow here. So we found our VI. Now what we can do is we can plug that back into our equation for Vy initial velocity. So the change we found earlier that, did we find this right? Yes, we found earlier that the change in top, the change in time to the top is Vi sine theta times g. If we plug back in the vi, then we can find the change in time to the top in our original constants without our velocity. So let me just clear up some of the space on here. We plug in square root of g times x top over sine theta cosine theta times sine of theta over g. And this equals our change in t top. Now, that gave us both our initial speed equation and our change in t top equation. Thank you for your time.